something.
So you have a k plus 1 here. Why don't you need a k plus 1 here?
I do.
Now that everyone's here.
You have lecture notes and the problem sets under the resources bar.
Excuse me?
You have the lecture notes and the quizzes, the problem sets under the resource.
Yeah.
And
Uh-oh. Sava says it's not in the resources.
okay.
Oh.
Previous time I saw on the weekly concept, so I could download from there.
Pardon me?
From the previous ones, I could see on the weekly concept, so I was downloading. But
God, I don't understand. Okay.
Don't worry, if it's in the Dropbox folder, I'll get it all in.
Yeah, I have no idea. It may not be in there.
Okay.
Okay, well, I'll take care of it right after. What about the final experiment? Is that? I wonder if that's. I wonder if that's in there. Well, let's not worry about that right now. Let's just worry about experiment 3. Okay. Okay, so this is problem set 7. We're going to do a couple problems in chapter 7 and a couple problems in chapter 8. And then later I'll send out a quiz, which is just on chapter 7. And that'll be due Wednesday. Thursday's Thanksgiving. Next Thursday's Thanksgiving.
Not next Thursday, the following. Yeah, that's 2 weeks.
Huh. Okay, so my calendar's wrong. No, I must have made a mistake. So yeah, this seemed too early for. Okay, so.
do you make any plans for it?
Yeah, I'm gonna have to.
I'll have a turkey 2 days. I'm good with that.
Yeah, it just seemed kind of early. Okay, I screwed up this morning. All right, but I haven't sent it out yet, so I'll fix that. Right, okay. So, okay. All right, so the first problem here is chapter 6.2, and we have a circular piston. It's baffled in water. And we're given this information. It's radius. This is the frequency. And we're given the pressure, peak pressure amplitude on the axis in dB. So the first thing you do here is you find Ka, because we have that information. You don't, as I've mentioned to you before, you don't really need to worry about what the problem is. Excuse me. You don't need to worry about what the problem is. You just got a dimensionless numbers. Going to be almost always important. Specifies the radiation pattern. So we use omega is equal to ck to get this. Omega is 2 pi f, right? So plug the numbers in and we get 8. So is that large compared to 1? Well, it all depends. I think we've talked a little bit about this before. It depends what kind of accuracy you want. We're going to only make this approximation much greater than 1 at the end, and I suspect it's a pretty good approximation there. It's going to be in the directivity. But you know, if you're curious, or if you're worried about it and you encounter it, we have the exact expression for the directivity. You know, often you can do that, so you can compare to see if that approximation, right, this approximation works well. Okay, so the first problem here, anyway, is to find the, we know that in the far field we're going to have nodal cones, right? So we have this, I don't know how to draw this, baffled piston here. Here's the axis of symmetry. And we know that in the far field we're going to have cones here. Where we have 0 pressure, okay, nodal cones. So we're going to solve for those. And we've done a similar thing before. I don't know if it was a baffled piston or not, but we definitely did it for the line source. Same Same idea. Of course, the geometry is different. Remember the line source, the cones are like this. They're going to be about the axis of symmetry. Here's the axis of symmetry. So we've solved for the directional factor, the far field, directional factor h, and it involves Bessel functions. There's Bessel functions with extra damping in there. And when you set the, when you look for the pressure nulls, you get this relationship. Ka times the sine of theta is equal to J1, and this is the nth zero of the J1 Bessel function. This is standard notation around the world, okay? Little j for the zeros, 1 for the order of the Bessel function, n is the number of the zero here. And they arise because the directional function involves Bessel functions, and we're looking for where it's zero, so it involves the zeros of the Bessel functions. So these you look up. These are in the textbook, in the back of the book. So here they are to 3 and 4 figures here. So we just invert this. We just find the angles. We've done a similar thing before. And we get these, and there's, you don't really, you know, depending upon the frequency, the higher the frequency, which means the smaller the wavelength, the more nodal cones you're going to get. Eventually you run out of nodal cones. You don't need to worry about calculating that. You can just march, normally we just march along here and calculate these, and eventually we find that we've run out of them. There will not be a theta 3, because you can't have a real angle that has a sine greater than 1. Okay, the next problem is to, find the peak velocity, well actually they want the RMS velocity of the piston. So we can get at that through this formula for the axial far field pressure. And you actually don't have to, we derive this, but there's a quick way of getting it. I don't know if you remember. If you think physically here, in the far field, along the axis, everything's going to be in phase. All the sound from all these little elements, all these little elemental sources of sound is all going to be in phase when you're far away on the axis. When you're off axis here, you have phase differences, right? You can actually get perfect destructive interference. But on the axis, they're all in phase in the far field. So you can actually use the general formula for a small source. Now, that's a little dangerous because we don't have a small source here. And you know we don't because we have nodal cones. A small source would be radiating isotropically here. But we can, as we've encountered before, you can actually use that formula. And then you put in just, it's a general formula in terms of the source strength, capital Q, and that's just the volume velocity. So it's U naught times the, so if you substitute this into that, you know, general formula, you'll get this. It's another way of getting at this, okay? So what do we know here? We know that so many dB, it's 100 dB with this reference value. So what that means is I've got 100 dB, and the dB measure is 20 times the log to the base 10 of the peak pressure, which is what we're given, and I need to divide by square root of 2 because the reference here, this is always RMS here. So I got to divide by square root of 2. So I can invert this, right? This is easy. Just bring the 20 over here, exponentiate to the power of 10, and you can isolate this axial pressure, and this is at 1 kilometer, incidentally, and we get that peak pressure. And once we've got that, we can now substitute it into here, and we can find the velocity of the piston, the peak velocity of the piston. So that's straightforward. Plug the numbers in, and I get 2.3 meters per second. And they ask for the RMS, so we divide by the square root of 2, and we get 1.6 meters per second.
Can you have just solved for the RMS out of the SPL equation?
Yes, you know, it's funny. I thought somebody might ask that when I was looking this over last night. You can do that, yeah. And so you can probably guess what my response is going to be. Yeah, you can save yourself a little bit of writing, okay? But I wouldn't do it. It's too easy to make a mistake. I know it sounds trivial to you, but I think some of you now have encountered this in the lab where you make little silly mistakes, and boy, if you know, you can pay a big price there. So you always want to look at things simply and check yourself. But you're exactly right, you can do that. We could have avoided, we went kind of a little circuitous here, or whatever the word is. But this is the way I would do it. I'd be very careful about this. Very simple. So part C is, what happens if we double the frequency but keep the drive amplitude, the velocity amplitude, the same here? What's going to happen to the axial pressure? Well, at first guess you might think, oh, nothing's going to happen to it because we're not changing the amplitude of the drive, right? Well, we're not changing, we need to be careful. This is simple harmonic, this is simple, going in simple harmonic motion. We're not changing the velocity amplitude, okay, of the drive. But that's not right. And from a physical perspective, the reason it's not right is, if I keep my source strength the same here, but I increase the frequency, what's going to how directional? What's going to happen to the sound field? It's going to become more directional. So that's not a proof, but it's an indication that the amplitude is going to go up on the axis. And for the mathematical proof, we just have to look at the formula here. Here's our axial pressure. We're keeping this constant. Everything else is constant. K is proportional to the frequency. So if we double the frequency, we're going to double the pressure on the axis, keeping U naught the same. So the axial pressure will double. What's this change in sound pressure level when you double the field? Well, some of you know this. It's approximately 6 dB. And you know, people who use dB a lot don't even think about this. A doubling of the pressure is 6 dB increase. The careful way to do it here is this change in sound pressure level. We went through this, we've gone through this before several times, do you remember? And I skipped a step here. The change in sound pressure level is the final minus the initial. The final is 20 times the log of this divided by the reference, right? When I subtract off the initial, the difference of the logs is the log of the quotient, so I get this. And like I said, we've encountered this before. So I didn't write all that out here. So the pressure's been doubled, so we get 20 times log 2. And this is close to 6 dB when you punch it in on your calculator. So finally here, there's the directionality. The directionality is approximately given by this for large Ka. And you know, the natural question is here, well, how large does it have to be? Well, you know, I don't use this in research, so I don't know. But again, if you're concerned about this, we have the exact formula for the directivity of piston. We have it, right? It's in terms of J1, first order Bessel function. So you can calculate it and compare, and I've never done that, and no one's ever come to me with it. So if you do it, let me know. It's interesting, you know, it's mildly interesting how well of approximation this is here. So we have 8, so this is going to be a directivity of 64 approximately. And you can see here that if we double the frequency, we're going to quadruple the directivity, because it's squared here, right? The directivity index is defined to be 10 times the log of the directivity. And so the change in the directivity here, because we're quadrupling it, and again, it's the final minus the log of the final divided by the initial. That's a factor of 4. So this is identical to this. 10 times the log of 4 is identical to 20 times the log of 2. It's about 6 dB. So we're getting the same same change in decibel level for the pressure and for the directivity. And I think, you know, the reason, what's behind that is the fact that what we started off with by saying is that we'd expect the pressure amplitude to go up because we're changing we're increasing the directivity here. And in fact, they both go up the same. The directivity in dB, they both go up the same in dB. They both go up 6 dB. The directivity index and the sound pressure level both increase by about 6 dB. Questions? Okay, the next one's in air. Okay, and I promised you we would do this. I don't know if you remember, but here's what this problem is all about. Okay, first of all, let's set what's going on here. We're in air, piston radius, this frequency, find Ka, and what do you see here? Okay, and they clearly designed it to be near 1. I would bet a lot of money that K or F or C or S, or a combination of them, wanted to end up with Ka close to 1. So now we're out of luck as far as approximations go, I would think, okay? So the small Ka approximation shouldn't work well here at all, and neither should the large Ka. How badly they don't work, I don't know, I haven't calculated, but if you get interested and you do it, let me know, okay? All right, so what's the first question here? It's to find the amplitude, velocity, the peak velocity amplitude of the piston, okay? If we have an acoustic power output of 1/2 watt. So what do we know here? Well, we know, and this is always true, regardless of what Ka is, that the total acoustic power is 1/2 the peak velocity squared of the piston times the radiation resistance. And you don't need to look that formula up, right? It's the same as a resistor. Okay. So this is a very convenient formula, and all the complication is buried in this radiation resistance. And here we have to actually look it up. So if you go back and look at the theory, you'll see that the radiation resistance exactly is expressed as this the high frequency radiation resistance, rho naught C times S, which is pi a squared. This is what we get in the high frequency limit, as we've discussed many times, right? Small wavelength. The impedance, the radiation impedance will be purely resistive in that case. No reactance. And then there's this dimensionless function here, which R1 involves J1, I think it involves a first order Bessel function, I can't remember. But you can look this up in an appendix, table A6 in the back of the book. These values are tabulated, right? So we need to double Ka, which gives us about 1.81, and then look up R1 for that value. And oh, interestingly enough, it looks like my question has just been answered here. How close are we to the short wavelength limit here? It's quantified right there. Can you see it? You might think, well, look, I'm just going to assume high frequency, even though this is not much greater than 1. It's probably going to be roughly right. Well, how much is it off? Can you see it in the math there? It's right here, right? In the high frequency limit, this R1 just becomes 1. So you can see it's a factor, you know, it's like we're down by a factor of 3. And we're down, definitely, because, you know, the higher frequency, the more radiation, you know, the more coupling you have to the radiation field, the less the radiation resistance is, the greater the radiation resistance is. Okay, so we get, for a given amplitude, we get more power. at the high frequency. So we're down by roughly a factor of 3 here. So that's nice. That's good. You can see. So it's nowhere near close. You know, this R1 is really not near 1 at all. Okay. Okay, so we punch these numbers in. We get this. Everything's in SI units here. Is typically what I do, at least. When I write units, I understand that it's all in SI units, and radiation resistance is mass per time, so it's kilograms per second here. Well, once we know that, see, that's all the complications buried in here, right? And the nice thing about impedance is you don't have to go through what's behind all this. You just use the result, you know, in this simple expression right here. So when we do that, we invert this, and we find 0.31 meters per second. That's the peak velocity amplitude of the piston. Now we can even go deeper. So this is connecting the drive with the response. The response is the acoustic field, the acoustic output. And now we're connecting the drive with that. But we haven't gone all the way, have we? How do I know what's behind this? How do I get this? Well, I get it by exerting a force. Almost always, the way we think about this, and for this transducer here, I'm going to exert a force on here. What's the force? Okay? So we can answer that question. I think we've done it once before. We're going to go through it again. I think maybe twice, can't remember. We're going to go through it again. But I just want to try to impress upon you the importance of this. This is sort of the bottom line here. The goal is to link up from a transducer point of view here, the drive with the response, to connect the two. Now, in case I forget, we're going to find the force here, but have we gone all the way? Think from a practical point of view. You're on a ship, you know, and you need to know something, or something's broken, or I don't know. You want to know what's going on with this black box that you have here. Is it the force amplitude? Is that the ultimate drive amplitude? No, what is it? How do we get the force? Well, usually it's from some electrical. You know, we're going to put some current. And, you know, for a loudspeaker, we're putting current through a voice coil. And we're driving it, right? So ultimately, it's going to be electrical. That's our friend, right? Mechanical stuff is hard to deal with. But electrical stuff is pretty straightforward. We can have equivalent circuits. Well, that's the subject of 4454. Okay, making the final connection with the electrical side of the transducer here. We're just going to go to the mechanical side here. But ultimately, we would want to go to electrical. But that's going to have to wait for another course. So how do we get to this mechanical connection here? Well, here's what we're given. Here's the actual mass of the piston, sometimes called the bare mass, or just the mass of the piston. And the reason you want to be careful with this is you know that because the wavelength is not very small here, there's going to be some reactance due to this fluid. It's going to cause a mass loading here. So the external agent, which ultimately is going to be an electrical circuit, right, that's driving this thing. Right now we're just going to think of it as us doing this, but ultimately it's going to be electrical, right, is going to feel, it's going to see a mass here that's greater than the actual mass there. So that's why some people sometimes use the word bare mass to emphasize that it's not the total effective mass. Here's the stiffness. This is a harmonic oscillator, damped harmonic oscillator. The damping's negligible in this case. So what do we do here? Well, the first thing we do is we're going to find the contribution to the mass, the inertia, due to the fluid here. And it's the radiation reactance divided by omega, the angular frequency, as we've seen many times. Okay. So here again, we can't make an approximation. We can't use one of these, x here, the argument is neither small or large compared to 1. So we can't use those approximations. We got to look it up in the it'll be tabulated in the back. I didn't even say it here, but it'll be going right along with this. I think you'll see it in an appendix. So again, we evaluate x1 from the table approximately at 2 Ka, just like before for the radiation term factor. and we get a number here, and it's this. It's 8.7 grams, which doesn't seem like a lot, but you can see it's roughly half of the actual mass. So it's going to make be a difference here. So the total effective mass is the sum of the two, and we get this.
Sorry, so the 0.613, is that 2K8?
Uh-oh. Where did I get that? Yeah, where did... I'm claiming here, and I didn't check it, I'm claiming that if you go to the back of the book and look at x1 at twice this value, you're going to get 0.63.
Oh, that's x1. Okay.
Yeah.
Yeah. Thanks.
And incidentally, I don't know if I've told you guys, but you know, over the years, I've just naturally done this. Write all of this stuff out. And we do it you don't do it in a journal article, okay? You very seldom can you do that in a journal article, okay? But in theses, I think it's a great thing to do. You can see the calculation here, you know? So Dan could have eventually figured this out, okay? It's possible. Because, you know, I really like this. And I notice a lot of some instructors, they'll just go right to the number here. I think it's really useful. So I actually almost insist upon this in theses now. It takes up a little bit more space, but it can be really useful to see. And one of the reasons it's useful is, you know, is this right? Well, I guess here, you know, we can look it up in the back of the book. Oh, no, it's an even problem. Well, we have some solutions here, right? And, well, this is the solution. But, you know, you wonder, is it right? And in a thesis, you're doing research, and, you know, there's no answers in the back of the book. There's no book. So how do you know you're right? Well, you worry about this. So here you can easily check it once you've typed this in your thesis. You can easily go back and check this, because you're going to be checking it again and again. You want to make sure it's right. So I think it's a really good idea to write all this out. And some people may say, well, yeah, you ought to put the dimensions on there, but that gets, to me, that's going beyond something. Gets too cluttered to put the dimensions. I understand here everything's in SI units, okay? All right, so now that we've got this effective mass, now what do we do? What links the drive with the response? What's the ratio of the drive to the response? It's the impedance, right? Always. Impedance always has that kind of form. So the impedance seen by the external agent, the electrical circuit, ultimately, that's driving this thing, the total impedance is going to be, these two add in parallel. You see that the impedance of this harmonic oscillator here and the radiation impedance. So the total impedance will be the sum of the two. I've skipped a step here. The resistive part, the total, you know, resistance here is going to be the sum of the resistances. So there's a mechanical resistance, which is negligible. There's a radiation resistance, which we've found. We calculated that earlier. And then I've added the two reactances here. This is the due to the mass, and this is the reactance due to the stiffness for a harmonic oscillator. And I'm going to convert to frequency here. That's easy. And then I'm going to plug the numbers in. Everything's in SI units, okay? I'm going to plug the numbers in. And now I have some complex algebra to go. I'm just going, well, it's already done. I'm just going to evaluate these things. Actually the imaginary part here. So in the end, we have the total impedance here, seen by the external agent, driving this piston. And it has a real and an imaginary part. And there's phase information in there. We just care about amplitude here. We want to find the force amplitude. So in my impedance relationship, the impedance being the complex drive divided by the complex force, I take the modulus. I take the amplitude. Because that's all I care about are the amplitudes here. I don't care about the phase. So what's going to be important here is the modulus or amplitude of this. And by Pythagoras, it's equal to this. So I end up with so many newtons. It's amazing. No, maybe it's not so amazing. I mean, think how long it's taken us to get to this point, right? And you have to include a fair amount of last quarter too, right? Impedance that you did. So it's deceptive here. You might think, oh yeah, this is simple, but it's taken us quite a while to make this connection here. But it is, it's one of the ultimate goals here. We want to link the drive with the response. And we want to go the other way too. This is a transmitter. We want to be able to handle receivers too. So that'll be much more on that. We don't do a lot of that in this course, but we will in the 44-54, the transducers course. Yeah, question?
The reason we use 2 Ka is because it's not, Ka is not large or less than 1, right? Part B, X1.
Right,
Ka,
right.
so it's close to 1. That's
Oh, maybe what you're asking is, yeah, it's actually close to 2. Yeah, but it's still not a very good approximation to assume that this is, this is going to asymptote at large argument here. It is, there is a 2 there that just naturally comes out for some reason in the math. So we are kind of getting towards the asymptotic limit, but we're not, the asymptotic limit, this will be 1, right, as we said. So we're not there. I think that's too crude of a, right. Does that answer your question?
Yes.
Okay. Okay, so next we have just a couple of Chapter 8 problems here. We talked about viscosity yesterday, and viscosity causes a phase lag in acoustics, as we mentioned yesterday. And here, or not here, went the wrong way. Here we're going to, so there's a characteristic time for the acoustic variables to respond to some kind of pressure gradient, if you want to think of that as sort of the drive here, which is what we often do. There's a characteristic time there due to viscosity. There's a lag in the acoustic variables. So we're going to find that characteristic time for glycerin. Here is the so-called relaxation time we talked about yesterday in terms of the viscosity coefficients. This is the bulk viscosity. This is the shear viscosity. Here they don't say it, but we're supposed to assume that the bulk viscosity is approximately 0. This is not always the case. We'll talk more about it later next week, okay? Which is not Thanksgiving week. I just want to let you know. Sorry. So we're going to assume that the bulk viscosity is 0. And what we're going to do here is just plug in some numbers, go to the appendix. You'll, these, I don't know about your books, but my books they're definitely, if you look at the edges of the pages, they're kind of dark around where the appendices are. Because you look stuff up there all the time. It's really good that they're there. So you look up glycerin, and you can find the density and the speed of sound, the shear viscosity. So you just calculate it, and it ends up here being quite a small number by our everyday standards. It's less than a nanosecond. It's 4 times 10 to the minus 10 seconds. So, so that's an indication that for typical sound waves, that they're not going to attenuate very much. And in fact, this is our common experience, right? I mean, you're listening to me right now, and there's not a huge attenuation. There's very little attenuation in my sound amplitude, right? However, what's important here is the frequency compared to this. You're going to have, as we showed yesterday, you're going to have substantial attenuation when omega times tau is equal to 1, roughly in that ballpark. So we can find the frequency for which we have substantial, rough frequency for which we have substantial attenuation here. We set omega equal to 2 pi f, and we just solve for f here. And it's 400 megahertz, okay? So in glycerin, that's a wavelength of 4 microns. So it's pretty It's pretty tiny, okay? Now, you may think, if you remember what we encountered yesterday, was for a gas, typically this wavelength is less than the mean free path. So the whole fluid description breaks down. The continuum fluid mechanics breaks down. Now this is a liquid though. So what's the mean free path for a liquid? Well, a liquid, as we think of it as molecules or atoms, sliding. The mean free path is, comparable to the size of the molecule or the atom, I would think. So, and this is not near there. So, I would think that our theory would work here. It's not, we hit this problem with a gas yesterday so KFCS kind of snuck it in there so we wanted to make this approximation because we can then come up with analytically simpler expressions, okay? And they motivated that by saying for a gas, you have to make that approximation because otherwise the theory is not going to hold. But here, I don't think the theory will apply here. And now that I think about it, I think long ago I think I've seen studies of attenuation of sound and liquid. I think you could push on the theory here, and try and to verify this. I think it should work. I think the theory should work here. But anyway, if we are in the low frequency limit, which would be natural here because this is such a high frequency, we can then use this expression that we derived yesterday for the absorption coefficient. So this is the thing, the absorption coefficient, a traveling wave is going to decay, the pressure amplitude, if you like, is going to decay exponentially. And this absorption coefficient is that coefficient right there. And here's the formula for it in the low frequency limit. And you remember I told you yesterday that it's proportional to the square. Remember the elephant thing? Proportional to the square of the frequency. If anybody finds out information on those early elephant studies, let me know. I'm sure it's in the literature. It was a big deal, and it'll resurface every once in a while, this kind of thing. So it's proportional to the square of the frequency. So if you wanted to, you can't really tabulate this because it's dependent upon the frequency. So what people do, and it's in KFCS, what you'll see tabulated is the frequency squares comes over to this side of the relationship. So what's tabulated is the absorption coefficient divided by the actual frequency squared. That gives us something that's independent of frequency, so you can tabulate it. And what we get here is we calculate this. We know these numbers, right? Yeah. We know these numbers, we just calculated, and I get 4 times 10 to the minus 12 second squared per meter. Okay, that's the absorption coefficient divided by the square of the frequency. Now, in KFCS, they've tabulated this, and there's a significantly different value. And this is not the only place where this can happen. I don't know if I can't remember if it occurs in 3119, but it sometimes comes up. Here, often what it's due to, and it's not just this book, other books, sometimes values, these values, where are they here? These values sometimes will change, people will refine these values, the density, the speed of sound, and so sometimes that can make a difference, and they can change it in one part in a book and not another part of a book. But something worse is going on here. If you look at that table, it looks very suspicious. I invite you to look at it. They list all the values as like 3, they go to some exponential here, it's like 3000.0 or something. It's obviously, somebody wrote that in thinking they were going to change it later. And they never did, even though this book's in its 4th edition. But Steve's looking up, if you find that table. So it's in the chapter. Not in the
Oh,
back of the
okay.
book, sorry. Yeah, it's in the chapter, embedded in the chapter. Anyway, it's very suspicious, okay, this value that they give. They give it to way too many figures. There's no way there's going to be significant figures there. And they say that the experimental value is identical to, there's something screwy. So I wouldn't worry too much about this. Something happened there. I'm pretty sure they just never got around to editing it. They said, oh, let's write it as some ridiculously precise value and all the same. That'll clue us in that we need to change this. And they never did. You see it there? Yeah, it's weird.
Yeah.
Okay. Okay. So, yeah, it's
3000.0.
yeah, 3000.0, right, yeah. Right. Okay, any questions about this one? It's sort of a plug-in. Now, this problem is actually interesting. I'm going to try to convince you this is interesting. It doesn't start off looking very interesting, but I learned something from it when first time I saw it. So I'll explain that to you. So here this is 2.3. From this set of equations, I'll tell you, those equations are simply equation of continuity, linearized equation of continuity, linearized thermodynamic relationship, between the pressure and the condensation. This comes from the thermo, it's linearized. And then the third equation is linearized Navier-Stokes equation. Okay, the standard equations of fluid mechanics here, linearized for acoustics. So we want to deal with, you can see what we're after here. We're going to deal with a decaying sound wave here. Okay, it's a plane traveling wave. It's decaying exponentially. So we have some dissipation. Clearly there's some dissipation. I guess I should point something out here. This is not necessarily due to viscosity. There are other effects that give rise to attenuation that will amaze you, that we're going to get to. So we just want to realize here that we have one or more sources of absorption of sound, or attenuation, yes, loss, acoustic loss. We have this, you can see the energy is going down, okay? And in fact, how would you expect the intensity to go down here for this plane wave? Remember what the intensity is for a plane wave? It's the pressure amplitude squared over 2 rho naught, what is it, rho naught c squared? Hold on, I can check this while thinking about it. Sorry. I'm off dimensionally here. So everybody, and I think I can safely say everybody here, unless they'd worked through this problem, okay, would say, well, you just take this and substitute it into here, and you're going to get e to the minus 2 alpha x, no big deal, right, because it's intensity. And, and we forget about this, we just care about the pressure amplitude, right? This is average intensity, which is an average quantity. So you would certainly expect that. The amazing thing is that it's not exactly true. I was really surprised by this. I should point out, though, that in most cases, because typical acoustic, almost most acoustic waves don't attenuate very rapidly compared to the wavelength example. That's often what we compare it to. So often, because the amplitude is going down slowly here, you can think of this as in space. It's decaying slowly compared to a wavelength. This will work, as we'll see. But from an exact point of view, that's actually incorrect, which I thought was really surprising. So that's sort of the point of this problem, part of the point. So we know that this has to be true. So the first thing we see here is that there's the pressure and the condensation are going to be exactly in phase, okay? So that's what the thermo tells us here. Assuming this is not modified by the loss mechanism. There is actually an assumption here. We are, now that I think about it, we're making an assumption here. Okay, but we're told to do that. Continuity, linearized continuity in one dimension boils down to this. So we know that the condensation is proportional to the pressure, so I can just plug that in there. I get this. We can then, I went ahead and substitute what the pressure is, okay, and took the time derivative. So we can integrate this with respect to x to get the particle velocity. And right? Now, when you integrate this with respect to x, it's convenient to combine these two terms. You know, you just say that you're just integrating e to the something times x, which is 1 over that something times the exponential. You know, we can easily integrate an exponential. So there you see, that's there for the chain rule. Okay, and then we recognize we're getting the pressure back here. This and that are just this pressure. So we're going to call it this. It's convenient to call it this. We've got this extra factor that's emerged here. All right? And we want to think of, we're going to think of small attenuation here. And again, small means that it decays a little bit over wavelength. That's equivalent to alpha over k being small. So this quantity right here in the denominator is small. Well, 1 over 1 minus a small quantity is approximately 1 plus a small quantity, right? We've used that many times. It's a standard approximation. But it's interesting. And we've also, you also are all familiar with this approximation, right? There's a dot here. You're all familiar with this, right? Well, interesting enough here, it of course also works going this way, right? So it's convenient for us here to identify a phase angle. This is one of these unusual situations where instead of making an approximation going this way from here to here we want to recognize that this is approximately that. Okay? Oh, and incidentally, I never forgotten the first time I saw this. I was a graduate student. I was TAing for Schwinger in his quantum electrodynamics class, for which he shared the Nobel Prize, and he did this. And it blew us all away, because you know, you just never, but it's obviously true, right? We do this, nobody has a problem with that. Well, you can go this way too, as long as that's true. So it's convenient here, and the reason it's convenient is we can then, we then easily identify the phase angle between, there's going to be a phase here between the particle velocity and the pressure. And their phase angle is that. So we see here, because this is positive, the particle velocity actually leads the pressure by this phase angle alpha over k. And this is accurate for small attenuation. Okay, and I want to point out they don't ask for it here, but the impedance here is no longer, it's, you know, we think, oh, plane traveling wave, impedance rho naught c, not with the dissipation. It's now become complex because there's a phase angle between the pressure and the velocity, right? So what's the point of all this? Well, the point is the intensity is given by this, okay? Now, because this is a product of quantities here, we've got to take the real part before we take this product here. So here's the particle, the pressure is given to us, it's specified. Here's the particle velocity, and we've got this phase here. I take the real part, I get the cosine of alpha over k, right? So what's this cosine of a small quantity? Right. So the cosine, I guess I'll use z again. And this is for, okay. So to first order in our small quantity, the cosine is just equal to 0. Because the cosine is a maximum at 0. It's flat up there. So it's not changing much for small alpha over k. So to first order approximation, the cosine of a small number is just 1. So when we do that, we get this. Oh, no wonder you're looking at me strange. We want to put that there, right? Sorry. Yeah, so way back in the beginning. I should have had this in there. Sorry. You guys need to tell me these things. Okay, so.
If that's P naught squared, then yes. But otherwise,
Oh.
it's just in that P.
Yeah, sorry, this is supposed to, okay, you're right. You're right. Yeah. So you're right, we're okay. This was actually technically okay, but I should have written this. Make it explicit. So we do get that, but the amazing thing here is that it's just an approximation. If you go to the next order here, you're not going to get this. That blew me away. And I always thought it was obvious, you know. So again, I think it's unlikely this will come up, but you know, I'm sure people have done research where they have strongly attenuated acoustic waves. You can imagine in applications where that might come up, right? If you don't want to be detected by a sound wave, you want to absorb acoustic wave on it, you want something that will highly attenuate the sound. Right? Remember, you want, first of all, if you have some material here, you want to be able to match the impedance here so that you don't get reflections off that interface, right? And then once the sound wave gets in here, eventually it's going to hit something else and come back out. So you want it to attenuate quickly. So there is certainly a need for strong attenuation in acoustics, right? And so I should say there's very fancy modern techniques that maybe you've heard about for cloaking, right? That actually caused waves to bend around an object rather than to try to absorb. That's hard to absorb sound on an object. People have been working on that for decades, right? And the radar problem too. It's a similar radar problem. But there are people are now investigating ways in which you can actually cause to refract the wave with so-called metamaterials. You guys heard of that? Yeah, so this high-tech stuff is on the way. Okay, that's it. So lab at 3.